I was working on deploying one of the large language models on AWS, and one challenge was how can I reduce the latency? There are different large language model operations practices, tooling, and infrastructure to see how different components help overcome the challenges of these large language models. I want to talk about compression, how to shrink, trim, and approximate the model to get it as small as we can. Compressing models to as small as we can make them will improve deployment time, reduce latency, scale down the number of expensive GPUs needed. There are several methods to compress the size of the model, like quantization, pruning, knowledge distillation, and low-rank approximation. In this video, I want to talk about low-rank approximation. It's also known as low-rank factorization, low-rank decomposition, matrix factorization, that uses linear algebra tricks to simplify large matrices or tensors to find a lower dimensional representation. There are several techniques to do this: singular value decomposition, SVD, Tucker decomposition, TD, and other methods. I will talk about SVD. We show the general idea behind the SVD method. Essentially, we are going to take a very large matrix A and break it up into three smaller matrices, U and sigma, S and V, while U and V are there to ensure we keep the same dimensions and relative strengths of the original matrix, and S, which is this sigma, to apply a direction and bias. The smaller S is, the more we end up compressing and reducing the total number of parameters, but the less accurate the approximation becomes. So this is the example of SVD. Again, this is a low rank approximation. A is a large matrix with dimensions n by m. We can approximate it with three smaller matrices, U with dimensions m by p, and S is a square matrix with dimension p times p, and V with dimensions n and p. Here, this is a V transpose. In the next slide, I will show you an example of SVD at work compressing. So U contains left singular vectors and S contains singular values. V transpose contains right singular vectors. And I will say that K equals 1. So instead of computing all singular vectors, SciPy, which I'm using here in this example, returns only the largest singular value and its corresponding singular vectors. This is known as the best rank 1 approximation of the matrix. If you run the cell, so this is the matrix, and it is 4 by 4, so it has 16 parameters, and this is the output. We will get 9 parameters. So we shrink here the memory footprint almost by half. So here, the U, the singular vector of the shape 4 by 1. This is the U, 4 by 1 column. And the S is singular value, which is 38.62 of the shape of 1. This is the magnitude of the strongest pattern in the matrix. And finally, this is the V transpose, the right singular vector, which has the shape of 1 by 4. This shows the dominant direction in the column space. The U shows the dominant direction of the row space, this one. So a singular value is like how much energy or variance the matrix has along a particular direction. Large S means strong dominant structure in the matrix. And finally, we multiply the matrices back together to get the original matrix. In this case, the approximation isn't all that great, as you can see. This is the original A, it's 2.2. Well, the original one is 1. And that's why we don't use it in the prediction style. Most likely because of the poor accuracy of the approximation. What we use is adaptation and fine-tuning, which is here, call it low rank adaptation, where we use it in the production. Adaptation is the process of fine-tuning a generic or base model to do a specific task.